Hello and welcome in E equals insa. In today's edition we will reintroduce you with some basics elements of this year's lessons of physics. We'll add to it a bit of experiments and applications to the real world. All the subjects we'll discuss today will be closely related with aeronautics and space conquest themes. First, we'll speak about weightlessness, which is the sensation of no weight. An object in weightlessness condition is an object which, put on a scale, will indicate 0. It's an object which is under the force of gravity, just gravity. So there is no counter-reaction of any other object, such as the floor, the road, or the air itself. So if you are standing in the only gravity, you can apply the second law of Newton, which says minus normal reaction more weight mj is equal to 0, all in vectors. But if you're not standing in a place where there is just gravity and the counter-reaction of a support, then you'll see this 0 disappearing for an acceleration ma. If you carry on this calculation, you'll have minus Rn in vectors is equal to ma in vectors minus mj in a vector, which brings us to Rn is equal to mg minus a, all in vectors. And this is this very equation which explains all about weightlessness. You see, if the A is equal to J, which happens when you're in free fall, this part is just equaling 0, which means Rn is 0 too. You feel no counter-reaction of the ground, and that's why you're not feeling the weight. This very situation is very obvious in, let's say, a spaceship in which the astronauts are falling toward the Earth without the counter-reaction of the air. But this situation can be reproduced on Earth with a plane. Here is the plane. To begin with, you will be in a level flight, then climb up at nearly 50 degrees. Nearly up this climb, which will be a parabolic flight, you'll cut off the gas. The acceleration of the engine goes away. You'll be, as this equation says, in only acceleration of j. At this moment you are in weightlessness. All the objects are in weightlessness. A few seconds later you'll be diving, and as the dive carries on, you'll put up the power to stay in another level flight. At this very moment, another acceleration than gravity is applied, and you lose the weightlessness conditions. This very parabolic flight is what I'm going to show you. See you on the field. For that, we'll need some objects to levitate, a plane, and a camera. We're now ready to reach for the skies. And climbing at 6,000 feet. We're now in the level flight, getting a bit of spin, and setting in the climb at 50 degrees. We're now nearly up the parabol. Weightlessness will soon appear. It's appearing now. It's now time to set in a new level flight. We'll show it again to you with a G meter for you to see the G approaching 0.
crashing in a bad way. But I found your local laughter, so just let's stay where yours in the first place.
So now that we've reached the second part of the emission, I will introduce you the notion of quantity of motion. So, thanks to the conservation of quantity of motion, the rocket can reach the space where astronauts can encounter the situation of weightlessness that Edward explained us before. So for a given system you have a quantity of motion P that equals mv, and the second law of Newton brings us that sum of forces equals ma. So sum of forces equal dp on dt. Sum of forces for an isolated system is equal to 0, because force are equal and opposite. So dp on dt equals 0, that shows that the quantity of motion is always constant. Now we have a rocket standing still on the ground, so we have a quantity of motion of a whole system, which can be divided in two under quantity of motion, the quantity of motion of the rocket and the quantity of motion of the fuel. The quantity of motion of the rocket has its proper mass and velocity, and the one with the fuel ejected has the same thing, which is its proper mass and velocity. The addition of the two quantity of motion is equal to 0, because the rocket is standing still, so the two speeds are equal to 0. So from this equation, we get this equation by putting the quantity of motion of the fuel on the other side of the equal sign. So we get a minus, because the velocity of the fuel ejected is oriented downwards, and the velocity of the rocket is oriented upwards. So by developing the quantity of motion, we get this equation. So this is equal to this in module, and because the thrust is constant, the mass of the fuel and the velocity of the fuel ejected are constant, so this part is constant, but the interesting thing is down there. We have the mass of the rocket, which is going down because of the fuel inside of the rocket being burned, and so this is going down. So to match with this part of the equation, the velocity of the rocket must be going up. So this explains us why the rocket is constantly accelerating when she is wanting to reach the sky. So now I'll let you with our experiment with a train propelled by a balloon on its roof, which is the same principle of the conservation of quantity of motion, but in our experiment it's oriented horizontally. This is the only thing that changes. So let the images speak now.
So what we've done is making a rocket engine out of a cylinder of cardboard, in which we put a balloon, using the thrust of it and the loss of mass with the implicated gain of velocity, which is a result of the conservation of quantity of motion. At first we reached a speed of about 20 centimeters per second, but with some improvements we made a 10-meter long run with 3 times the speed. We hope you enjoyed the time you spent with us speaking about physics and aeronautics. See you next time!